Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions online and get answers, join our lectures. You can find the link to Discord in our Telegram channel. Find out the schedule of the lectures, join our Telegram channel. Today in this session, we will start talking about the different types of load on applications. Specifically today we will talk about rebound load. This is certainly the load when there is a lot of data input-output in the application, but there are no significant live computations. Why is it necessary to know all this? This is necessary to write optimized applications and to effectively use the resources of the system in which we deploy our application. So, as I have previously mentioned, the very first one is I/O bound load, or input and output load. What problem arises here? Our application resources, primarily the processor, are idle. And it is idle at the moment while our application is waiting for data from some external components. What could this be? It could be another application, a service. For example, we sent a request to some API and are waiting for a response. We sent a request to the database and are also waiting for a response from the database. Well, overall, if we are doing something with the network, then it is definitely U-bound load, because we will always be waiting in the network, even if we are sending something over localhost, like TFSP. This also involves working some external devices like files, but that's the most obvious. If we are working with the file system, for example, reading or writing something to a persistent storage device, such as a hard drive or SSD, there are also waits in order to ensure that the data is properly and securely handled and stored. There is definitely not much load on the processor, but it takes time for some old hard drive to spin up.
Want to become a great programmer? Subscribe to our Telegram channel.
And it processes the necessary data for us, records it, and time will pass. This time is idle time. Our program will use it inefficiently, because idle time can always be occupied with something, especially if our program doesn't just start, run. This is, for example, some kind of service. Requests go to the service. And because of this, there will be challenges and potential problems with wait time loss. Let's take a look at the images to see what I/O bound actually represents. Here, a request comes into our application, as a result, in the system. We have very little time. The processor is extremely overloaded, like 1/100th of a second. At this moment, let's say we send a request to another server. Then we wait for a response, and we wait for this response much longer than the time spent by the processor here and here. Here, our processor is idle. And then, when we receive the response, we process it. Here, our processor is also loaded, and this is also negligible compared to the wait time,
TFSP.
1/100th of a second. From this, it follows that the request time, the execution time of the request in our application, is approximately about around 1 second. We will typically disregard these hundredths of a second because they are generally not comparable to 1 second, and they are typically considered negligible. Now, let's take a closer look in detail at what exactly happens if multiple requests simultaneously come into our application. The first, second, and third requests, these requests came to us at the same moment in time. That is, so to speak, in parallel. One of the requests starts to be processed, let's say the first one, and it takes 1 second to execute. Then, at the same moment in time, at 0 seconds, we received the second request. But it will only start executing at the moment when the first one finishes. That is, essentially, the second request will start executing only here. And in the previous second, it was simply just patiently waiting, awaiting for its own turn to proceed with the process. And the third request will wait till the first two requests are completed. And here at the end, after the second one finishes, it will only start executing then. So what will happen? The first request that will be processed will be completed in 1 second. Overall, this is how we initially planned it. The second request, since it was waiting for the first, will be completed in 2 seconds. It will have 1 second of waiting and 1 second of execution. Third request will take 3 seconds in total. It will have approximately 2 seconds of waiting and 1 second of execution. Accordingly, the more requests we send to our application in parallel, the execution time of these requests will grow linearly, predictably. That is, the first request will take 1 second, the second already 2, the third 3, and the fourth. Well, as you can clearly see, accordingly this is not acceptable because, in reality, in fact, our request is processed in just 1 second. It turns out that the average processing time can actually go to infinity, depending on how many requests we have coming in at one moment. This means that in certain situations, the system can become overwhelmed, leading to potential delays. This is not good. Well, here is a simple example of an application that effectively models this particular situation. This is a function that allows processing a request. Then here I have a function where I send a request to the server and wait for its response. But instead of sending, I just put a time sleep, setting it to 1 second. Here it returns to us like this. And also, here is the code for parallel request sending. We won't look into it too closely. It can just release back into our application in parallel. That's it. If we initially run our application and then the script for sending requests, we can see that our first request was successfully sent, received a response, and it was completed in approximately 1 second. Then, the second request, which was sent simultaneously at the same time, will take approximately 2 seconds to complete in total overall. The third request takes 3 seconds, the fourth takes 4, and the fifth takes 5. So indeed, the response time for requests sent at that moment grows nearly 1, 2, 3. And each request is processed in a manner that is 1 second longer than the previous one. This is absolutely not considered acceptable by any standards. It's absolutely unacceptable because, based on this picture, we completely comprehend that the resources of our system are not being utilized at all. It would be nice to somehow utilize that whole 1 second. In principle, during this 1 second of waiting, we can try to make an effort. Process almost 100 requests. TFSP. One of them is waiting, and there are still 99. During this particular period of time, they will certainly indeed be able to send their messages. So what exactly are we doing? We need to ensure that during this idle time, some other tasks or activities, such as reading, organizing, or planning, for example, can be performed. The standard approach to usually optimizing IEO load for us in practice is either synchronization or concurrency. If you want to learn what synchronization is, what concurrency is, as well as the parallelism of synchronous program execution, then subscribe to the channel, but we will cover this in a couple of lectures. Here, we look at such large, detailed, and comprehensive examples within the framework of this system in detail. And in general, what do both of these approaches allow? They allow the processor to be used for performing other tasks, while one of these tasks is waiting. For example, we have 3 requests that come in at the same moment. Here, we only have the execution time when the request starts executing and when it finishes. Here, the first one has arrived, and the processor is busy, so other tasks cannot be processed for now. The processor is busy. Here we very briefly send a request for 0.01 seconds and then wait. Here the processor starts to stand idle. As soon as it starts to stand idle, we can begin to perform other tasks. Therefore, we take the second request here and occupy the processor with it. Well, we occupied it for a while in order to send a request. In this case, it starts waiting again, and now both are waiting. we can take some third task.
Want to become a great programmer? Subscribe to our Telegram channel.